Good afternoon, everyone. Welcome to the week 3 live session Structural Dynamics. In the last 2 weeks, we studied free vibrations of undamped systems and the equations, equilibrium equations associated to it. In week 2, we also solved some basic problems related to the single degree of freedom system. Uh, I'm going to give a little bit recap of what we did in the last week, that's week 2, and then we will start with this week's topics, that is the damped free vibrations. So in last week we solved this equation: max double dot plus kx is equal to 0. So this was free vibrations only, okay? Vibration only. So if we include the damping into it, damping of the system into it also, so we have to add one more term, that is Cx dot plus Kx is already there, Kx is equal to 0. That will be then damped free vibration. We saw the solution for this mx double dot plus Kx is equal to 0 as uh, displacement time history as x of t was given as a cos pt plus b sin pt. This was the solution that we obtained for the above equation. And we also derived it, derived this also in short form like this after combining both sine and cos terms after making some proper substitution. We had x of t as c sine t of t plus alpha. Okay, where we made the substitution: a is equal to c sine alpha and b is equal to c cos alpha, and b is equal to c cos alpha. After making these substitutions, we obtained a sinusoidal variation, and also a time period. We note that P was the natural frequency, already I mentioned it, and natural time period. Natural time period we obtain it as T is equal to 2 pi by T, and uh, T is equal to under root K by M, and coefficient of the stiffness term divided by the coefficient of this initial term, under root K by M. to 2 pi, so we have to take the inverse, it will be 2 pi and root m by k. This was also there, and corresponding frequency will be p upon 2 pi to 1 by 2 pi and root k by m. Okay. This we derived last week. Okay, so we saw the variation also, these two constants a and b after putting the initial conditions as the system is starting vibrating from the rest as x of 0 is equal to 0, and no velocity is important. So x of x naught of, if we will not take it as rest conditions, but there are some values for these initial conditions as At t is equal to 0, it was having some initial distance x naught, and at t is equal to 0, it was having some velocity as v naught. So after making these substitutions in x and x dot, yeah, we obtained that a was actually coming to be x naught and b was actually coming to be v naught by p, v naught by p. So a is having the dimensions of length, and here we can also check which is the dimensions of length. Velocity is length time inverse, and p is also time inverse. Okay, so we can write our solution x of t as, in terms of initial condition, the x naught cos pt plus v naught by p sin pt. Yes, sin pt will be there, sin pt. Okay, so this is the solution obtained after including the initial condition in our problem. So this one. So if we try to sketch the graph for this x of t called x naught cos pt plus v naught by p sin pt, we will have like this variation like this one. So example, we have this thing x here, and we have this x, this y axis. So if we try to sketch the graph like this one, since it's a sinusoidal variation here, we can say sin pt plus alpha. Okay, can have like this. Okay, like this one. So we are seeing that, right, after every fixed time interval, this solution is coming to have a maximum value, like this one. This we term as amplitude. They are like this. We term, let us denote it with capital X naught. Capital X naught we can derive it like this. If we see the function x of t is equal to v naught cos p, cos pt is there, or is sin pt. Cos pt plus v naught by p, v naught by p, it's x naught here, sorry, x naught, x naught cos pt v naught by p sin pt, sin pt. So we have to check in a maximum solution. We know for this type of function x of t, maximum, for example, we have y is equal to something a cos x plus b sin x is the function. We try to make a value as y max as something additional is 1 to a square plus b square. Okay, so it's something this. So we can write here similarly, x naught x of t max, we denote it as x naught, capital X naught will be equal to under root of no, okay, this will be equal to uh, x naught square, this is over a square plus v naught upon p whole square. Okay, this will be the expression for the amplitude of our free vibration motion. So we will check here now in the graph. X naught we reduce it. So for initial conditions, if we are starting the motion from zero, we will show it here. Motion is from like this motion is from starting at t is equal to 0. Yes, this is t is equal to 0. We will be seeing at t is equal to 0. It is having some value. This one, that is our initial condition that we incorporated into the equation, that is x naught. And initial condition at t is equal to 0, we were also having some slope. That's the value of the b here. So if we see that initial condition here, where not here exactly, let this correct it a little bit. So it's like this. Okay, and then variation like this. We're having it like this. So we can see that this is x naught, and this was x naught. Okay, up to this point, initial displacement to the system, and we are having slope here also. If we draw a tangent to the at this point like this will be our initial velocity of the system, like this one. Okay, here its value. Its slope will be equal to, so it will give us maybe a note there. Okay, initial conditions while we incorporate into our solution. Okay, and this phase angle first alpha will be given by, here we can see where we made our substitutions, like here this we can have alpha from these two equations there. Mm, alpha will be equal to mm, tan alpha, in fact tan alpha is equal to a by b. Okay, we'll take it here. Tan alpha equals a by b. A by b. Our a is x naught. Okay, a naught by b. So solution. Also, one more thing, in the free vibration is the energy associated with the free vibration motion. We also saw that. Free vibrations. Again, free vibrations will be energy in free vibration will be the summation of kinetic energy and the potential energy. It will be kinetic energy plus potential energy. It's a total energy. It will always remain constant. Okay. Kinetic energy will be changed into potential energy, and potential energy will be changed into kinetic energy. Total energy will remain constant. Okay. Kinetic energy is 1 half of m x dot square, and potential energy is in fact the strain energy in the spring. Spring energy 1 half of kx square is called constant. Okay. So we have also one more method of deriving the equilibrium equation of free vibration motion. If we will differentiate this equation now, yes, differentiate with respect to x, we will get back to the equilibrium motion equation of motion. 1 by 2 m twice x dot into x double dot, okay, plus 1 by 2 k twice x into x dot, product rule is equal to 0, okay. If we take x dot common, we will be left over with m x double dot plus kx is equal to 0. So from the energy principle, we can also write the equation of motion for a free vibration system. These things are already discussed, so I thought to give a little bit recap of these things. So today we will be discussing this one. So what if the damping is also present in the system? Looking at the vibration of damped single degree of freedom system. Okay. For example, we have a system like this. Block of mass, block of mass, and like this. Let's connect it here like this. We have spring connected to it. Of spring constant K, and we also have a dashboard. It's like this. Okay. Of dynamic constant C, and this is the direction of the motion of our block of mass. Okay. We know the governing equation of motion will be, okay, governing equation of motion, Gm will be mx double dot contribution from the inertial force, cx dot contribution from the damping force, plus kx contribution from the stiffness of the system, be equal to, since it's a free vibrations, no force is present there, will be equal to 0 from the equilibrium. So dividing throughout by m, we will be left over with x double dot plus c over m of x dot plus k over m of x is equal to 0. We will make some substitutions here. As substitute, we will put p as equal to under root k by m, or k by m is equal to p square, and also we will write c by m as twice the p. We will make these substitutions where theta is the damping ratio. Okay, x double dot. I will tell you later on what is damping ratio. It will be equal to twice theta p x dot plus p square x is equal to 0. And here from we can write theta as c by 2 mp. We can also write it as c by 2m and p as under root k by m, will be, which will be equal to c by twice m, twice root mk. These are the alternate expressions for the damping ratio. Some of the important factors in the vibrations of damped single degree of freedom systems. Okay. One more thing is that initial conditions are given. X at 0 will be something x naught, let be, and x dot of 0 will be something v naught. Initial velocity and initial displacement of the system will be given there. So we will assume that solution has the form x is equal to r power t, x is equal to e power rt. Okay, so we will check this whether this assumption is true or not. We will deduce x dot will be r e power rt, and from this equation we need x double dot, and similarly x double dot will be r square e power rt. Okay, simple differentiation. When we substitute these things, okay, when we substitute these things, okay, back to this equation here. Okay, we will obtain we will obtain r square e power rt in place of x dot. Okay, plus, not in that equation, sorry, we'll put in this simplified equation. Okay, this one. Okay, we have to put it in there. We will obtain r square e power rt twice theta p e power r times e power rt plus p square e power rt. Okay, it will be equal to 0. If we take e power rt as common, we will be left with r square plus twice theta pr plus p square equal to 0. Since these are the two factors, and for this equation to be 0, one of them at least has to be 0. So if we take e power rt as 0, so we are assuming the displacement as 0. This will not be the solution. No? E power x is equal to 0. That is e power rt is equal to 0. So among e power rt and this another factor, this one, this has to be 0. That's r square plus twice theta pr plus p square should be equal to 0. Okay, so this is the quadratic equation in terms of r. Solving it, we can have two roots as r1 comma 2. Two roots will be equal to minus b is twice theta p plus minus under root b square minus 4ac. B square is twice theta p ka whole square minus uh, what is 4ac. C is p and a is 1. 4p square divided by 2a is 1. Huh? Okay, when we solve this further, we will obtain r1 comma 2 is equal to minus theta p plus minus under root theta square minus 1 minus 1 times p. Okay, we take p as common, r1 comma 2 will be equal to p times minus theta plus minus root under theta square minus 1. Okay, so we obtain these two roots for that equation. So actually, the values of r as per this r is these two roots of this equation, that's r1 and r2, will decide the type of damping that will occur in our system. Okay, so we will see what are these types of dampings. So there are two solution these roots of this equation. So we can write auxiliary equation as x is equal to solution as, in fact, the auxiliary equation we can write solution as x is equal to c1 c1 e to power r1t, since both are distinct, so it will be c2 e to power r1t r2t, where c1 and c2 will be found from the initial conditions. Okay, uh, we can see here that from this equation can make something like this. You can see if theta is greater than 1, r1 comma r2 both will be real and positive, sorry, real and negative, real and negative. Okay, if theta will be less than 1, r1 comma r2 will be imaginary. Okay, and at theta exactly equals 1, both r1 equal to r2 will be 1 minus 3. Okay, then we have case first. Now we have three cases: theta greater than 1, theta less than 1, theta equal 1. We'll take the first case. Case first, theta is less than 1. Okay, so in when the damping ratio is less than 1, what we call this type of damping motion as light damping, call it as light damping, or we also call it as under damping, under damped or subcritically damped, subcritically damped motion. Okay, so we have theta less than 1, or 1 comma 2 will be equal to p times minus theta, uh, plus minus, plus minus, you will see if this theta is less than 1, this root will give a negative value. So for this term to be positive inside the root, we will introduce uh, imaginary number iota, that is under root minus 1, iota times 1 minus theta square. Okay, the solution will be like this, general solution. General solution will be like this: x of t will be equal to a1 e to the power r1 t plus b a2 in fact a2 e to the power r2 t. Okay, so r1 and r2 we will substitute back there. X of t is equal to a1 e to the power r1 is equal to p minus theta plus iota root 1 minus theta square. Okay, so and a2 e to the power p minus theta minus iota times under root 1 minus theta square. Okay, this is very simple. If we take here, you can see that this is plus here, so these are product terms. We can take e to the power minus theta p comma theta p, sorry p, theta pt comma e to the power minus theta pt common. We are left with only a1 e your power iota under root 1 minus theta square. Okay, and that also p times t. Okay, plus a2 will be minus iota times e power minus iota times 1 minus theta square. In fact, it's root and p times t like this. Okay, so if we introduce here, replace this term, that is p under root 1 minus theta square divided by 1 minus theta square by another term pd, we will obtain x of t is equal to e power minus theta pt a1 e power pdt iota pdt plus a2 e power minus iota pdt. Okay, this thing where pd is this one, we call pd as dampness. You can see, okay, because the damping is also associated with the natural frequency, so we replace it with the damped natural frequency. Then we have this, we can write for e to the power iota pdt and e to the power minus iota pdt expression is like this one. Because we know this e to the power, Euler's formula na, e to the power iota theta is equal to cos theta plus iota sin theta. Okay, so by the aid of this expression we can write PDT, treating PDT as theta. Okay, we can expand the cover iota PDT. So we can have x of t as e to the power minus theta pt a times a1 times in fact cos pdt plus iota sin pdt plus a2 cos pdt minus iota sin pdt. Okay, like this thing. Okay, so when we rearrange the terms, we get this thing: e power minus theta pt a1 plus a2 a1 plus a2, collecting coefficients of cos pdt terms dt term and collecting coefficients of sin pdt term iota sin pdt. Okay, We have to collect the quotients for this one also. We have to write quotients will be a1 minus a2. Okay, here it is minus a1 minus a2 like this. Okay, we can again replace this. Let me put it in oh, another color. A1 plus a2 divided by a and a1 minus a2 as b because these are only constants, so we can replace them. Then any other symbol x of t we will obtain then x of t we will obtain then e power minus theta pt a cos p dt plus iota p sin p dt. Sorry, we are taking this whole as b. Okay, we are taking plus iota a1 minus a2 as b. Okay, we will write here then b sin p dt. Okay, so this we obtain the solution for our damped free vibration system. Okay, then as I already mentioned, the initial conditions are x of 0 as x naught and x dot of 0 as v naught. So to get a and b, we have to induce these initial conditions in the above equation. Okay, so when we take these two initial conditions into this equation, we obtain a as x naught, similarly as the previous one. And for b, there will be a slight change. When we do things, we will obtain b as v naught by pd. Initially in the free vibration, undamped free vibration, it was v naught by p. So here it is v naught by pd because it is damped. Okay, plus some additional term will be there due to the damping effect. Theta p divided by p times under root of 1 minus theta square. Okay, this will be there and times x naught. These are the constants a and b. Okay, so writing them back into this equation. In fact, pp will be cancelled here. Okay, pp will be cancelled here. PP. We will have then x of t as x of t will be equal to e power minus theta pt minus theta pt x naught cos pd of t plus v naught by pd plus theta times under root of 1 minus theta square x naught sin p dt of t. Okay, this will be the complete solution of our problem, damped free vibration. Okay, you will be seeing in this course once we are inducing more and more effects like because initially there was no damping. The equation solution was little bit shorter. Now we induced the damping. Equations are getting longer and longer. So when we induce one more factor, that is the forced vibration, equation will be more longer after that. So these effects are inducing more complexity into mathematical formulations. So this is a sine and cos variation in our solution, but since there is a decaying term also associated with it, look, you can find the decaying term as e to the power minus theta pt. So decaying term, okay. So the decay of the motion in the damped free vibration will be governed by theta and p. You can see and the damping of the system, okay. If the damping is more, the system will come to rest at very small amount of time, and if the damping is very less, the system will take more time until it comes to rest, okay. So we will sketch the graph of this solution as like this. For example, this is uh, y coordinate, this is our x coordinate, okay. So the decay of motion will be like this. It will be having some initial displacement and initial velocity like this, but it will be continuously decaying due to the presence of damping in our system, okay. So the motion decays like this, and we have a decaying pattern like this, okay. We actually note down the equation of this decaying pattern. It will be exactly equal to this line will be dashed line will be having the equation rho times e to the power minus theta pt. Okay, and this line is the point of the tangency of all the peaks. So now damped time period will be from this peak to this peak. Okay, like this we are having td damped time period 2 pi by pd. Okay, so for example, after n cycle it was having amplitude xn here. Now after n plus 1 cycle it's having amplitude xn plus 1. Okay, we are having damped time period td as equal to pi by pd. Damped natural time period. Damped natural time period. It will be equal to 2 pi, and initially we know the value of pd as p times under root 1 minus theta square. Okay, so since theta is less than 1, 1 minus theta square will be even more less than 1. So this is 2 pi by p is actually the natural time period Tn divided by under root 1 minus theta square. So the denominator is getting less than 1. So we'll be having Td greater than Tn. So the damped natural time period will be greater than the natural time period of damped time period will be greater than the natural time period of system. Okay, damped time period will be greater than the natural time period of system. Okay, and one more thing we will see for the circular frequency. Initially, we designated PD as equal to P times under root 1 minus theta square. Since theta is less than 1, 1 minus theta under root out 1 minus theta square is less than 1. So, damped circular frequency, damped circular frequency will be less than natural frequency. Okay, these are the main points to note. Okay. So we found the damped natural time period and damped time period and the damped circular frequency. And we found that the damped time period is greater than the natural time period and damped circular frequency is less than the natural circular frequency. Okay. And one more thing, the practical range of this damping ratio is theta is less than 0.2, or we can consider it as 20%. Okay. Practical range. Okay. Now we have to see the decay of the motion, or the rate at which the motion decays in the damper free vibration system. Okay. We found that was the rate of decay. Rate of decay of motion. Okay. This one. We find that the x of n at any point of time is given by e power minus theta pt, and it's a complex combination of natural frequency and the damped frequency a cos pt plus b sin pt, b sin pt, where a is equal to x naught, that's the initial displacement, and b is a complex term that I wrote here, is equal to v naught by pd plus theta divided by 1 minus theta square times x naught. Okay. So if x of n is the amplitude after nth number of cycle, and we want to write the amplitude of the same motion after n plus one cycle. So x of n plus one will be equal to x of uh, n plus, we have to add one more time period. Okay, td, like this one. So I will show you like here in the graph how it comes. So we have here, for example, we have a motion like this, damped free vibration motion like this. Okay, we had this at, for example, at x of n, this motion. So this second motion was at x n plus 1. Okay, this one was, this whole was x of n. Okay, and this whole was x of n plus 1. So in between x of n and x of n plus 1, td amount of time elapsed. Okay, td. Okay, this one. So we have to add td to this x of n to get x of n plus 1. Okay, so we will write x, not this, not x, this time, this time versus displacement, that's x here. So we have to write x of n plus 1 as e power minus theta et plus td. Okay, damped time period. Time is a cos pdt plus td. pdt plus td plus b sin pdt plus td. Okay, like this. When we solve this, we obtain this expression like this one: xn plus 1 is equal to e power minus theta pt times e power minus theta p td. Okay, td, it will be like this. Okay, theta p dt. And since cos and sin are periodic functions, we will obtain this one: a cos p dt plus b sin p d t. Okay, because for sine if t is the time period, sine t plus t is for sine t. Same is the case for cos t plus t is called cos t. Okay, where is in this equation here? Get to it. Okay, so x of n we obtain this when we divide x of n plus 1 divided by x of n. Look, what is x of n? X of n is a cos p pt b sine pt e power minus theta pt. And this is e power minus theta p e power minus theta p td. Okay, this and this will get cancelled. We will be left with minus theta pt e power minus theta p td. Okay, divided by this one e power minus theta pt e power minus theta pt, and result comes out to be e power minus theta ptd. Okay, so we have xn plus 1 divided by xn now equal to, we will write e as exp now, little bit bigger, huh? Minus theta p, and td we can write as 2 pi times p and root 1 minus p square, 1 minus theta square, sorry. Okay, because td is equal to 2 pi by pd. Okay, damped circle, and 2 pi in terms of natural is p times 1 minus theta square. You have to remember these all terms. Okay, so we will use this relation here. Okay, so we obtain the ratio of successive decaying amplitudes as x of n plus 1 divided by x of n as exp of minus 2 pi. Okay, p and p will get cancelled. Theta upon root under 1 minus theta square. Okay, so we're having a decrement in the motion. So because x of n plus 1 is less than xn, so this term on the right hand side will be obviously less than 1. If we sketch the graph between x of n divided by xn with respect to theta, we will obtain a sketch like this. It's like this one. So if on this horizontal axis it is damping ratio theta as 0 0.1, 0 0.2, 0 0.3, 0 0.4. Remember, we take damping up to, in practice placing up to 0.2, that's 20% only. So this is xn plus 1 upon xn, and this is also some here like this. Yes, we'll obtain a graph like this, exponential decay of the motion. Okay, like this one. Decay of motion. Okay, this is like this one. So you can do one more thing to it. You can take the log on both sides. So if you take the log on both sides, we are left over with we take log on both sides. Taking log on both sides, we get log of xn plus 1 divided by xn. Natural log on both sides. So this will be equal to minus 2 pi theta upon 1 minus theta square and root of theta upon and root of 1 minus theta square. 1 minus theta square, okay. So we denote this log of xn plus 1 divided by xn divided by another term delta. Delta is equal to log of xn plus 1 divided by xn is equal to 2 pi minus 2 pi in fact theta root under 1 minus theta square, okay. 1 minus theta square, okay. This is known as logarithmic decrement. We term this as logarithmic decrement. A logarithmic decrement. Okay, this one. So since for practical cases we take theta less than 0.2, we can so theta is very less than 1 and theta square will then obviously be very much less than 1. We can tune theta to root under 1 minus theta square approximately equal to 1. Okay, when we induce it in the above equation, delta will be simplified to ln. So if we also uh, invert it, we will get ln xn divided by xn plus 1. And the minus will be cancelled from both sides. We will get this one. 2 pi theta. Okay. So delta is like this. Hmm, we can also sketch the graph between delta and theta again. I will give you the reason for why below theta below the value of point 0.2 we took 1 and root of 1 minus theta approximately equal to 1. So for example this is the graph of this is the graph sorry this is the graph of 2 pi theta delta equal to 2 pi theta, and this is the graph of uh, this is the graph of 2 pi theta upon and root of 1 minus theta square. It is with respect to theta and logarithmic decrement LD. LD delta, okay. So this point value is exactly 0.2. So for the values of theta less than zero point 0.2, it's good to take 2 pi theta rather than 2 pi theta under 1 minus theta square because both are having the same values. If we take theta above expression 2 pi theta upon 1 minus theta square, it will be more complex. So for uh, easy calculations, we take 2 pi theta, the Ampere ratio. Okay, this is logarithmic decrement. So I think this is all for today. Thank you.